Hi, this video is going to introduce what a power series is. This particular video just introduces kind of the theory and the background behind power series. I'll be making another video and posting it that has some examples of how to make them and what we use them for soon. But first, just the theory and the background. So the objectives of this video, basically know what a power series is, understand some of the basic ideas that go with a power series, and then we're going to talk about ways that you can create a power series. Like I said, this is just the theory part, so we're only going to talk about the ways for making a power series. I'll have another video that shows examples of how to actually do that. Before we get going though, I also want to take a second to talk about some strategies for learning from online resources, because that's something we don't do a lot of in our class. So as we start this video, a couple things to keep in mind. First and foremost, just like you would if you were in the classroom, keep those objectives in mind, because they're going to help you to understand how the material that we're doing connects to what it is that you're supposed to be capable of doing. Second thing is, don't forget this is a video. You don't have to watch it straight through. If I go a little bit too fast, hit the pause button or push the rewind button so that you can get your notes caught up. Next thing, stay mentally engaged. It's just like you would in class. If I ask a question in the video, obviously it's rhetorical because I can't hear your answer, but that doesn't mean that you shouldn't pause for a second and try and answer my question. Stay mentally engaged and stay on top of what we're talking about in the video. Which then brings the final point. If you're having trouble staying mentally engaged, either because I'm going too fast or because you need to take a break or anything like that, you can push the pause button, right? Push the pause button, go get a drink, stretch your legs, come back, and then resume the video. Or if I go through an example a little too fast, you didn't quite follow how it was I did all my steps, rewind it and watch that example again. Take advantage of the fact that it's an online source, which means that you can go back and watch it over and over again. Obviously, you can't ask too many questions until I get back to class, but there are things you can do to improve your learning. So let's start by getting into what is a power series. You don't have to have a strict definition of a power series, and because of that, what I'm going to do is I'm just going to introduce power series by looking at some examples. And the first thing I want to do is I want to go all the way back to algebra class, where you would have at least briefly talked about a power function. In fact, it might have been so brief that you don't even remember talking about it. Because typically in algebra class, once we talk about power functions for a little while, very short amount of time, we usually move right on into polynomials. So power functions are kind of like the most basic type of a polynomial. So here's an example of a power function. And let's talk about what makes this thing a power function. So that's one example of a power function. So what makes it a power function? Well, first of all, there's only one term in it. And then second of all, that term consists of a variable that's been raised to some power. So when we're talking about power functions, that's what we're talking about. Power functions are things that have the general structure of maybe a coefficient. Well, I mean, I guess you could say in one sense there's always a coefficient. Just sometimes that coefficient equals 1 or even 0. But so you got a coefficient, you've got a variable, and then that variable is raised to some power. And that's basically the structure that power functions have. So some other examples of power functions that you would have seen before are things like the cubic function, or things like the fourth power, quartic function, or other things like that. Now, in algebra class, you probably started with the quadratic, the squaring function, as the smallest power function that you discussed. But actually, at least as far as our class is concerned, we're going to have a broader definition for the power function. Our rule is going to be simply that P is a whole number. So P is an element of the whole numbers. Okay, that's going to be our definition. So if you remember, whole numbers, first of all, they're greater than or equal to 0. And second of all, there's no fractions and there's no decimals. Right? So we're talking about 0, 1, 2, 3, 4, 5, 6, those kind of things. Those are whole numbers. So those are the sort of options that we have for P. Anything that's greater than or equal to 0 that's not a decimal or a fraction when it's in its most simplified form. So I could, based on that, come up with some other examples. I could have, let's say, k of x equal to 6x. That would be like having x to the first power, which satisfies this rule. Now, typically we don't, when we did polynomials and power functions in algebra class, we usually put linear functions in a different category. But for our purposes, that's not a problem. We'll clump that in there also. I could even have maybe L of x equal to just a 5, the constant function. Why would the constant function be acceptable? Well, this would be the same as 5 times 1. And of course, 1 is the answer you get when you raise things to the 0 power. So this would be like the same as having x to the 0 power. And that satisfies our rule. So these are the ideas of power functions that we're going to work with in this section. And then, of course, power series, we know, is a sum. That's what series means. We're adding things up. It's a series. So if I take all these examples that I just wrote down and I put them together, so I had a 5, I had a 6x, I had a 2x squared, I had a 1/3 x cubed, and I had a negative 6x to the 4th. When I put those things together like that, that generates a power series. Now, when you look at that, you might say, hey, that's just a polynomial. That's no different than any other polynomial we've ever studied, except you wrote it backwards. And I suppose you're right. But here's the thing with a power series, and this will be true for every power series that we look at in the beginning of the chapter here. There's no rule that my power series has to stop. In other words, I could have an x to the 5th, x to the 6th, x to the forever. This could go on forever. I could literally have an infinite number of terms in my power series. And of course, when was the last time you had a polynomial with an infinite number of terms? That also explains why we write it backwards. With a polynomial, the rule was you started with the biggest exponent and you worked your way down. But if a power series goes forever, well, there is no biggest exponent because there's always another exponent that comes after that. So there's no way you could start with the biggest exponent. However, there will always be a smallest exponent. So you'll always be able to start with the smallest exponent and be able to work your way up. And so this will be the way that we work with power series. Now, that's not a good formal definition, and I know that, but this is a general idea of what we're going to be working with. And for the purposes of our class, at least at this point in the discussion, that's enough. Now, I want to take just a break for a second from a power series, and I want to revisit a different type of series that we've studied before, the geometric series. Okay. So a geometric series is something that we've talked about in previous classes, and we talked about a fair amount in the previous chapter. Geometric series, remember, is something that is kind of unique and kind of interesting in that there is a rule for a geometric series that tells us what's going to happen when I start adding things together and the number of things just keeps going and going and going and going. In other words, if I have an infinite number of terms. So in these two series that I have right here, you'll recall from previous classes in the previous chapter that one of them, that sum is just going to keep growing and growing and growing and growing, and eventually it's going to grow infinitely large, and we call that divergent behavior. That's what this top one is doing, and that should make sense when you look at it, that if I just keep adding bigger and bigger numbers, I'm going to end up with a bigger and bigger sum. So we say that this diverges. There's not a specific number that it's heading towards as it grows. But this sum, on the other hand, had the interesting property of the fact that it is moving towards a finite number. So 1 plus a half is 1 1/2, plus a quarter gives me 1 3/4, plus an eighth gives me 1 7/8, 1 15/16, 1 31/32, 1 63/64. That number is growing closer and closer and closer to a specific value. In this case, it's growing towards 2. And so this is something that we said converges. And what we meant by that is that as I continue to add more and more terms, the sum is getting closer and closer. It's converging upon the value of 2. And so we have this concept that sometimes, even though there's an infinite number of terms, I can still add up to be a finite value. And the interesting thing that we're going to use to our advantage in just a second is that a geometric series had two things associated with it. One was a rule to know whether or not it converges. And the rule was whatever you're multiplying by, which we called the common ratio, the absolute value of that number had to be between 0 and 1. And as long as the absolute value of the common ratio was between 0 and 1, then we knew that this sum was going to converge. Additionally, we could predict what it would converge to because we had a formula that said that the infinite sum, assuming that it converges, the infinite sum would be equal to the first term times the reciprocal of 1 minus the common ratio. And so these two facts right here are going to lay the foundation for our notes here today as we begin to discuss a power series. So keep those things in mind, and let's take a look at a series that's a general geometric series. In other words, if I have a general geometric series, I know that I'm multiplying by a common ratio over and over and over again. This is a general geometric series. That could literally represent every geometric series that exists. Now, if I were to tell you that in this geometric series, R obeys the rule for convergence, then we could say this general geometric series will be equal to the first term, which is 1, times the reciprocal of 1 minus the common ratio. And here our common ratio, well, that's obviously R. And so we end up with a formula like this. Now, it should make sense to you that R just simply represents some number that's in this range, which means there's nothing special about the letter R. I could use any letter. And so I'm going to make a quick little switcheroo, because typically in math class, we prefer to use an X to represent an unknown number, particularly if the unknown number can be any sort of number, decimal, fraction, rational, irrational, whatever. So I'm going to rewrite this with an X. I'm going to say that X is following our rule. And then if I do this, well, I can drop the 1, right? Because anything times 1 is just itself. What I end up with is this relationship. I want to think for just a second about the significance of that relationship. Go back to algebra class for a second. What is this thing? If we were in algebra class, if you were in algebra class and your teacher said, hey, we're going to study this function here today, what do we know about that function? Well, the kind of function that it is it's a rational function. We know it has a graph that has been, it's sort of related to this graph, right? The 1 over x graph, but it's been modified. Let's think about how it's been modified. I could rewrite this like that, which means I have this. So that means my graph, it's moved over 1 to the right, and then it's been flipped over the y, over the x-axis. It's flipped vertically. It's a vertical flip. So I've got a graph over here that's moved over 1 unit. So now my asymptote is at 1, and it's flipped. So the piece that was going down, now that piece is going up, and this piece is over here. Now that's nothing like a polynomial at all in any way, shape, or form. There's nothing like that that's polynomial-like. Okay? Now let's go back to that same algebra class, that same algebra teacher. If we were to write down this thing, what do we know about that? Well, that is a polynomial. And so we learned about things like polynomial end behavior, and when does it rise and when does it fall, and the fact that this would be the y-intercept, and all those sorts of things. And as we think about all the different kinds of graphs of polynomials that we studied, we know sometimes they go up on both ends, and sometimes one end goes down and the other end goes up, but nothing that's like this. But what this equation is telling us, as long as x is between 0 and 1, those two things are exactly equal. In other words, if we zoom in on this graph for a second, zooming in on that graph, if I'm between 0 and 1, and I graph this thing right here, I'm going to end up with the exact same identical behavior. Now, doesn't include the endpoint, so open circle. If I plug in 0, I get 1 over 1. So my first point right there, open circle, boom. And then I go to this thing asymptotically. And that graph is exactly the same as this polynomial's graph. And we could verify that by graphing both of them on a calculator. You'd have to type in a lot of terms, enough terms to overflow the calculator's memory. But if we were to graph those two things on a calculator, we would find that that's exactly what happens, is the one on top of the other. Okay. So why is that interesting to us? Well, notice what kind of series this is. It's geometric, yes, but it's also a power series. In fact, every geometric series is a special kind of power series as long as we're using it in terms of x's like this. This is a power series where every coefficient happens to be exactly equal to 1. That's not a requirement of a power series, but that's what this is. And that power series is exactly equal to this function over here. This function is the same as a series. The series is the same as a function as long as I'm inside of that interval. Now that's really, really handy, because think about all the things that you've done in algebra and calculus class. If you had to start doing derivatives, integrals, especially if you do lots of derivatives or lots of integrals, if you had to approximate the value of things with terrible, ugly, yucky little decimals and things, which would you rather work with? A nice polynomial or something that's like this? Well, generally speaking, polynomials are better. It's just easier to work with, especially if it's a polynomial where every coefficient is equal to 1. That's really easy to work with. And so this is the idea of how we'll use a power function. We'll use power functions to approximate functions that are, we'll use power series to find functions that are equal to, because these are easier to work with. And so they allow us to model this thing. And what we can do is we can say, well, they're exactly equal if we have an infinite number of terms. But if we just say, take the first 5 terms, for example, well, they're not exactly equal anymore, but are they close? They might be. They might be close. In fact, this is a trick that physicists play pretty regularly, is taking something that's, taking a function that's inconvenient to do physics with, and then finding some convenient polynomial to say, well, those are about right. In fact, the decimal places that it's off by is small enough that it's not going to make a difference. And engineers and physicists will play this trick pretty regularly in their mathematics. So that's the idea of a power function, where it comes from and how we're going to use it. I do want to take just a second to talk about ways that we can find a power function. So let's rewrite this equation again. Let's rewrite this identity again. So that is one power function. It's probably a power function that would be worth knowing and getting used to. Things that I can do. Well, this is an equation, right? An identity is just one kind of an equation. This is an equation. As long as I'm in the proper interval, these are exactly equal. So all of my rules of algebra that apply to equations, they all still work here. So for example, I can multiply both sides by a number. So if I wanted to find the power series that represents this, well, all I'd have to do is take this side and I'd just multiply everything by 2. And that would be equal still, because in algebra you can multiply both sides. Of course, you can also divide. You can also, you can do other things. Another thing I could do is I could make a substitution. Let x be equal to, I don't know, 4y. Then this thing becomes that, And on the other side, I'm going back up to my original up here. On my other side, all of the x's turn into 4y's. So 1 plus 4y plus a 16y squared plus a 64y to the third plus so on and so forth. So as I put in a 4y for x, first it's just a 4y. When I put in a 4y for x squared, I have to square the whole thing. So I square the 4 and I square the y. When I put it into x cubed, I have to cube the whole thing. So I cube the 4 and I cube the y, so on and so forth. So we can do basic math where we're just multiplying both sides or adding both sides or anything like that. We can do substitutions or composite functions where I'm replacing x with something that's equivalent to it. I can even do calculus. So let's say I was going to come over to this thing and take its derivative. Well, I think what I would do to take the derivative of that is, well, we could use quotient rule or we could use product rule. I'm going to use chain rule. I said product rule. I meant chain rule. I'm going to write it this way. So I'm going to end up with this going down by 1. And I've got to multiply by the old exponent. And so this becomes my derivative. Now, what's the power series that represents that? Well, if I just apply the same idea, that I can do anything I want as long as I do it to both sides, if I take the derivative of this side, the nice thing with polynomials is that derivative just distributes. So as I distribute it, I get the derivative of 1, plus the derivative of x, plus the derivative of x squared, plus the derivative of x cubed, and so on and so forth. And so what I end up with is a new power series that's equal to this new expression. Now notice this power series that I don't have constant coefficients. My coefficients change. It's a different power series, but it's the same concept as far as being able to set these two things equal to each other. Of course, if I can do that derivatives, I can probably also do that with an integral. So if I can integrate this and I can integrate that, then I can find a new function and a new series that are equal to each other. And I can go on and on and on and on with this. Okay, now, last thing to mention real quick is notice that all of these have an assumption. They're all built off of the assumption that I'm obeying this property right here. And so what we say is every power series that we find that's equal to another function, there's a specific interval where they're equal. And later in our class, we're going to talk about how do you decide what that interval is? How do you determine where exactly they're equal? This one was easy because the geometric series told us when they were equal. But is it the same for this? Is it the same for that? Are these the same? Well, that's something that we'll investigate soon. So that's the end of this video. So hopefully you know what a power series is and some basic information about it. And hopefully you can name a couple different ways that you could generate a power series. Watch the other video for more examples. Thank you.